Okay, so I haven't made out the exam yet, but I've started working on it. I'm mostly done. I can tell you that it'll have 4 questions. It'll have 1 free response from each exam. So the total, maybe 8, is probably going to be more because some of those questions had more than 2 parts. So I'll probably pick questions, well, I don't want to say that because some of the questions definitely will have 2 parts. But overall, they'll probably add up to more than 8 questions. 9, 10, 11, 12 questions, 12 separate parts. That's good for you because then you get, more points spread out. I think if you can do more questions in the 2 hours, then it's better for you. Probably the multiple choice is going to be 35 to 40. Like it's going to be on the high end. But, as I told you in class, I pull questions from the old test that I've mainly pulled conceptual questions, which doesn't mean that they're easier, but it does mean that you usually go through those more quickly. So you should have plenty of time, the 2 hours. In fact, I think that if you know it pretty well, it'll take you probably hour 20, hour and a half maybe. If you don't know it, you're going to sit there for 2 hours and, bang your head against, but that's just sort of life. Okay, so I have all the exams here. I'm going to send these out because I realized that the exam 3 is missing the first question. I brought it today so we can look at it. But I'll send a document that has all 4 exams. I would love for you to be able to sit down over the weekend and work through all the exams and make 100% on them, okay, without any help at all. I think that you would be pretty well prepared if you felt confident on every one of those 112 questions, okay? No, more than that. Yeah, 112 questions. But beware that if you study those exams over and over and over again, that it's going to be easy for you to just gloss over small changes. So like if I change a negative to a positive, for example, which is a reasonable change, then that might change the answer completely. So just on Monday, make sure that you take the time to read every single word of those questions. Okay? All right. Exam 1. So particular questions about exam 1. Yeah, Chloe?
Can we look at number 18 in spring 2020?
Oh, spring 2020. Yeah. So I just brought this semester's, but I can pull them up. It is useful to look at the past exams because often those questions are similar to, the questions that we've had. In fact, I'll tell you, I guess often my goal to be able to use questions from the final exam in some upcoming semester. So you might look back and see, like in spring 2020, a question that's similar to spring 2021. And often that's why, is because I've taken a question and I've sort of rewritten it a little bit. And that's why there's some similarity between those questions, because I do that.
I'm sorry, I'm at 16.
Number 16. Okay, so a person touches a Van de Graaff generator and their hair stands on end. Why? The reason why a Van de Graaff generator, I had a picture of it. Well, maybe we didn't. But a Van de Graaff generator looks like this. You have this belt that runs back and forth, and it runs over a piece of carpet. And this belt, just like when you rub your feet on the carpet, brings electrons up to this sphere. And then if you have a person that puts their hands on the sphere, then they get a bunch of electrons on their head. And when they get a bunch of electrons on their hair or on their body, those electrons all try to get away from one another. So they'll get electrons on the ends of their hair like this. And that makes their hair, stand on end. So here, the reason is they have an excess of negative charge. It's not B, that might be a question, an answer that you would think, but actually when you get charges on an object, those charges are evenly distributed. So on this person, they have negative charges all over their body, but they also have them on their hair, and it causes their hair to stand on end. Protons don't move, so it's not C, and they don't have an excess of positive charges. Just in general, positive charges don't move around. They're difficult to move because they're bound tightly to their nucleus. Okay, Chloe?
Thank you.
All right. Other particular questions? Exam 1. Yeah, Logan?
Well, I was going to ask you to do
This one right here. And, you know, we had a similar question on number 12. Like I said, this is a good example of a question that was in spring 2020 and then got pulled from spring 2020, and you found a similar one in spring 2021, and you might find a similar one in the final. So here I want to know, what is x? What is this distance so that the electric field here is equal to 0? Okay, so if you try to do this problem mathematically, it's going to be a little bit difficult because I'm going to have two electric fields down here. I have one that's in this direction, that's to this charge, and then I have another electric field that's in this direction, that's due to this charge. I imagine that I have a positive test charge at that position, and then I ask myself, what is the direction of the force that that positive test charge feels? Now I can write out the equation for these electric fields. The red one is going to be K times 2 nanocoulombs divided by 2 meters squared. And that has to equal to the blue electric field, which is going to be K times 18 nanocoulombs divided by X plus 2 squared. And then I would have to solve this for X. You can do that. We've never really solved an equation like that, but you should be capable of solving that. I guess you'd have to use the quadratic for that. But the easier way to approach this problem is to say, I have these two vectors that I want them to be the same magnitude. I want you to recognize that if this is Q1, that this is 9 times Q1, right? 18 is 9 times 2 nanocoulombs. So in order for those two electric fields to be equal, how much more must the distance be for the 18 nanocoulombs as compared to the 2 nanocoulombs? By what factor must its distance be bigger in order to account for the 9 times the charge? Now remember, the electric field is kq over r squared. So I have a factor of 9. Oh, sorry, give away the answer. I have a factor of 9 up here. What must the difference in the distance be in order for that electric field to be the same? Not 9, but 3, right, because it's a quadratic relationship. So the 18 nanocoulomb charge has to be 3 times as far away from point A as is the 2 nanocoulomb charge. Because it's 9 times the charge, it has to be 3 times as far away. And once I see that, well, I say this distance is 2 meters. That means that this distance must be 6 meters. And because it's 6 meters, then that means x has to equal to 4. That problem's a lot easier if you approach it conceptually, all right, not actually trying to solve the equation. Now, you could, I suppose, just put in numbers here. So, like, if I put in a 4 right there, does that work out? Well, I get a 1 over 2 equals 18 over 6 squared. Huh? 18 over 36, yeah, 18 over 36, which is the same as 1 over 2. So if I put in that 4 for x, I see that it's equal. But if you're actually trying to solve for x, it's not difficult, but you sort of get mugged down in, you know, quadratic equations, and I don't really recommend you do it that way. Okay, good question. I like this question because it looks like a math problem, but it really requires a conceptual approach, and I love it when you can do that. In fact, you know, most of the questions will require a conceptual approach, even if they look like a math problem. Yeah.
Can you go over one of the times where you have like multiple points between charges and you're trying to figure out which one has 0 force?
Sure. Yeah, let's see if there's one on this test. I think there was one in the old exam, right? I mean, this past semester's exam.
Number 18 on this semester's exam.
Okay, we can look at that one then. Oh, no, this isn't the one you're talking about, right?
No,
Yeah. This one's a little bit easier. Let's see. Like number 2, like number 2 there? Where is the net force 0?
Yeah, something like that.
Yeah, so here, if I place a charge, either positive or negative on the dashed line, where is the net force on that charge equal to 0? Whenever I approach these questions, like if I'm trying to answer them, I just start somewhere. Like let's start at the x, for example. Since these two charges are the same magnitude, maybe that's the answer. And then I draw the force vectors. Well, due to the plus 3 coulomb, I get a force vector that's in that direction. And then due to the minus 3 coulomb, I get a force vector that's in that direction. That's obviously not a zero force. In fact, once I see that, I can say that anything that is in between the two charges will not be the right answer, okay? Because I'm never going to get a zero force because both force vectors will be to the left. So it must be either to the right or to the left or none of these. So let's just try over here. I'm going to say the force due to that charge is going to be in that direction. And then the force due to this charge, it's in this direction. But note that it's going to be small because I'm farther away from that charge. Then I get a similar thing over here. The force due to this charge is in this direction, and the force due to this charge is small and in that direction. So neither of these are going to provide a zero force. The important thing here is that these two charges have the same magnitude. Now, if I change this problem a little bit, which I want to do, now let's say that instead of this being 3 coulombs, let's say I make this plus 12 coulombs. In this case, the answer is going to be, well, to the left or right, you think? To the left, right. So if I look over here, the force due to this charge is in that direction, and then the force due to this charge is also in that direction. It's a bigger charge, but I'm farther away from it. So those two, the bigger charge and the farther away distance, will balance one another out so that there is a position over to the left of that minus 3 coulomb charge where the force will be 0. Okay? Good question. I like those kinds of questions. I know that you do too, so I'm not saying what's going to be on there. I don't know what's going to be on there, but if I was looking at this, I would probably keep that question because I know that y'all like them. I like them. Right? There are some just straight up recall questions on the test, but I try to shy away from those. But I really want those sort of deeper questions, kind of like this one. This is a deeper question. Okay, good, 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 good. What else? Yeah, Tana?
Yeah, can you go to number 1?
Yeah, so another good, deeper question, because it looks at the interplay between the force and the charges and the distances. So on these, when or if you get one of these, you just draw the two component vectors. So here I have a 2q charge, a distance d away. They're both positive, so that is going to be a force in this direction. Here, I have a minus 2q charge, so I know that's going to be an attractive force, but notice that it's twice the distance away, so it's going to be 1/4 the force of the first one that I drew. This vector is 1/4 the magnitude of that vector because I know F equals kqq over r squared. Because I've doubled the distance, I'm on 1/4 the force. So when I draw those two vectors, I'm going to get D is the option. When I add those two vectors, I get one vector that's big, like that, one vector that's 1/4 it, and so the resultant of these two vectors is going to be closer to the bigger vector. Okay, it's not going to be a vector that's equidistant between the two. It's not going to be C. It's not going to be a vector that's closer to the smaller vector, either A or B. All right, good question. What else? Yeah, Rob and then David. On this test, yeah. Okay, so here, a couple of things that are important is what type of charge am I dealing with? And here, I know that electrons, remember I drew this picture in class? I said that if I have a mountain, protons tend to move downhill, as you know, as you would think of a rock rolling down a hill. But electrons do the opposite of protons. So an electron will move up the hill. That is moving from low potential to high potential. So if I have an electron at point B, right here, an electron is going to move from low to high potential. But look, it's already at high potential. So it's going to stay right where it is. It's going to stay at point B. Now, what if I had, I don't know, an electron right here? What direction would it move? It would move to the left towards point B, like it would try to roll uphill. Or like if I have an electron here, it would always try to get up to that high potential. Or if I had a proton, right here, it would roll, well, it would roll downhill in some direction. I don't know what direction it would move. I think that's right, because that's the steepest. But like if I had a proton right here, it would move in this direction. Or if it was at point D, it would just stay there. It's like it's sitting in the bottom of a well. Okay, we call that a potential well. And when you have a potential well, then you can hold those charged particles there. Okay, so on a question like this, I could change what type of charge it is, or I could change the map of the field of the equipotential lines, but then it's still the same process where you ask, am I rolling up or down the hill? If it's a proton, it's going downhill from high to low potential. If it's an electron, it's rolling uphill. I'm putting air quotes around that, okay? And so you're moving from low to high potential. All right, David? Number 6, sure. Okay, so I want to know the magnitude and the force on Q2. I love this question because I can look at it and see that the answer is, what do y'all think? Is 0, right? So I can look at it without actually calculating it and see that the answer is 0. Let me show you why that is. You can go through and calculate it, and that's fine if you have to do that, but let me show you. I have this charge right here. There is an attractive force between those two charges, Q2 and Q3. I'll call this F23. But then look, I have this charge over here, which is 1/4 the charge, right? So it's going to have 1/4 the force, but it's half the distance. Let's write out the equation. F is equal to KQQ over R squared. So if I look at this equation, I have 1/4 up here, but I have a half down here. That is, I have 1/4 in the numerator and a half squared, or 1/4 in the denominator, and so those are going to cancel out, and it's going to give me a force that's the same magnitude, but in the opposite direction. So that force is going to be 0. Now, if you don't see that right off, that's okay. You might not have seen that, but it makes the problem a lot easier if you do. But if you don't, you can just calculate them. You can say F23 is equal to 9 times 10 to the 9th times 4 times 10 to the minus 5 times 4 times 10 to the minus 4. Look, I even gave you nice, easy numbers so they cancel out right. Divided by the distance, which is 4 meters squared. And so that force, this cancels with that and that. This 4 squared cancels with those two, and it gives me a force of 9 newtons. So this is equal to 9 newtons. And then you could do the same thing for F21, and you would say, well, that's also 9 newtons. And since they're equal in magnitude, opposite in direction, then the force has to be 0 newtons. So 2 approaches. I prefer the first, but if you do the second, that's fine too. Okay. What else? Exam 2, can we go on to exam 2? We can come back to this, but let's look at exam 2. We have circuits, capacitor circuits, multi-loop circuits, combination circuits. Sonia?
Can you go over the
Sure. So whenever you're drawing these, and if you get a question like this, it won't be this circuit. It'll be something similarly difficult, but different. So I start on the positive side of the battery, and I start going through the circuit, and then I stop right here, and I say, what is happening right here? Notice that I have 3 branches that come out. I have 1, 2, and then 3 branches that all come together. I like to think of bringing junctions together. Since there aren't any devices along this path, or right here, or right here, or right here, I can bring all of that together, and I can redraw it so that it looks like this. I've redrawn that so that all 3 of those are together into one point. And then I can have my C1 right here, my C2 right here, and then notice on this rightmost branch, I have 2 capacitors going through that circuit. Then also notice that right here, it looks like a big jumble of wires, but since there are no capacitors or batteries or resistors, since there's no electrical devices in that part of the circuit, I can collapse it all down to a point. That means that I can take them all together, and it just looks like that. Then, as I come out of here, I go through that last capacitor, and I come up to here. So this is a 3, 2, 2, 2, and 3. Now at this point, hopefully you can see that I have some common numbers that I've seen before. These 2 and 2 together make a 1 microfarad, and then 3, 2, and 1 together make a 6 microfarad. So I'm left with a 6 and a 3. This is, I think it was a 12-volt battery. Yeah, 12-volt battery. And then the equivalent of 6 and a 3, of course, is 2 microfarads. I have a 2 microfarad with a 12-volt battery. That means that I have 24 microcoulombs. That means I have 24 microcoulombs here and 24 microcoulombs here. That means I have Q divided by C, or 4 volts, and Q divided by C, are 8 volts here. So now I have some of that information. I can begin to fill it in here. This is 8 volts. I have 4 volts that is over this entire branch. That means I have 4 volts here, 4 volts here, and then I have these two microfarad capacitors that split up that 2 volts, that 4 volts rather. So that's 2 volts and 2 volts. Once I get all those voltages, I can answer any question that I want if I'm asking charges or voltages or whatever. Okay? But of course, Sonia, you're right. The hard part is drawing the circuit. Once you get past that, if you remember those rules for capacitors in series and parallel, you'll begin to see those patterns, and you'll begin to see how those voltages are distributed. Okay? I will say, if I were to pick the free response, and I haven't done this yet, but I would choose either 1 or 3. These are more difficult questions than number 2, and I think they're more important. And also in the multiple choice, there are questions that are similar to number 2 that I can ask that question in the multiple choice. FYI, either 1 or 3. Was there a number 4 on this? 1, 2. Oh yeah, but see, there are 8 parts, so there are always 8 questions. Yeah. Yeah. I mean, you're going to have a multi-loop. You're going to have a capacitor circuit, so just be ready for both. Calculate the currents in the circuit. So you want to write your equations, right? We had this in the multiple choice too, where you have to write the equations. It's easier if you pick the right equation. And so you want to look for a branch that doesn't have a resistor in it. For example, this one, there's no resistor in it, or at least not in the bottom part of it. So if I write the equation for that part, it becomes easier. Let me just show you. I'm going to start right here. Oh, no, first, I'm sorry. Let's label our currents. I have I1 up here. I'm going to put it in that direction. I2, I'll put it in that direction. I3, I'll put it in that direction. No reason for choosing those directions. I just chose them. Doesn't really matter why. I'm going to start right here. I'm going to travel in that direction. So that's minus 6I2 plus 8 plus 2 equals 0. I'm going to go ahead and solve this for I2. That's negative 10 over negative 6 are 5/3 amp. So I2 is 5/3, and it's to the left. I know it's to the left because this came out positive, and so that means I chose the direction correctly. I can also make quick work of I1 if I do the big loop. I'm going to start right here, and I'll go in this direction. That's plus 4 plus 2I1. Why is it plus 2I1 and not minus? I'm going against the current. I'm going the opposite direction of the current. Plus 2, coming down here, equals 0. So that's I1 equals negative 3. That means I1 is 3 amps, and it's not to the left, it's going to be to the right. See, I had chosen it to the left, but since it came out negative, that means I chose it incorrectly. And then to find I3, you're going to have to use your junction rule. So I pick a junction. I see the incoming current is I2. The outgoing currents are I1 and I3. So I have those. But remember, you carry the negatives. So this is going to be 5/3 minus 3 is equal to I2. That's minus 4/3. So this is 4/3 amp to the left. Because I had chosen it to the right, it came out negative, so it must have been the wrong direction that I chose. I think I did all that right. Be careful when you're working these, just make sure you get, be careful with your algebra. What? Yeah, you're right. So I wanted chosen to the right, so it should be to the left. Chloe?
Can we just figure it out, how to figure out I1, I2, and hit the junction rule for another one?
No, you can't do that. She asked, could you figure it out like we did for I1 or I2? The reason you can't use a loop rule to find I3 is because there's no resistor in this part of the circuit. So you're always, at least in the circuit that I'll give you, you'll always need to use the junction rule. You need to know the junction rule because that's the only one that will give you one of the currents. And I say that, I don't know that you're getting this on the free response, but I'm just saying it's a good candidate. Somebody else had their hand up? Was that you, Courtney? Or that
Yeah, I was just confused on how you got the junction rule for it, because I think it says that before with 3, and it ended up being like 4/2 over 3.
Did I do it wrong? I might have just made a mistake somewhere. I did it wrong?
Yes, because, I mean, you found I2 twice. You found I2 twice.
Oh, yeah, okay.
So.
Yeah, see, don't be like me. Be more careful than I am. I was looking for I3, right? I'm supposed to be finding I3. So I3 is equal to I2 minus I1, which is 5/3 plus 3, which is 5/3 plus 9/3, 14/3. Is that what you're good? Okay, so that's I3 should be 14/3, not to the left, but to the right. Okay, good. I made an A. Yay. Okay. Fortunately, I don't get graded on the exam. I hate taking exams, don't y'all? Yeah. We should have, like, no exams. Okay. Let's look at some of the rest of this exam. Yeah, Megan?
Can you do 14?
Mm-hmm. Okay. This is a good deep question, right? Like one of the deep questions of life. What happens when you remove R2? When I remove R2, if I take this resistor away, the resistance of this portion of the circuit increases, right? That doesn't seem immediately apparent, but you're taking a path for the electricity to flow away from the electrons. That means that where before it saw two paths it could take, it now only sees one path. That means the resistance has increased. And if the resistance increases, since V equals IR, if R goes up, that means V goes up. So that means that V across this branch is going to go up. And I'm asking if V goes up, then V1 increases. By the way, V3 would decrease. That if V1 goes up, that means that V3 has to go down because they have to both add up to equal 12. You could go through and just work the problem asking what happens to the resistance across R1 if you wanted, but it's easier to think about it in that way. Okay, Megan? Other questions on this test? Okay, yeah, so again, you know, see a multi-loop circuit like here or in the free response or somewhere along the way. You want to know which of these equations are correct. So first, for the junction rule, you pick any junction. I see the incoming currents are I1, I2, oh, and I3. All of those are incoming currents, so it can't be that. It should have been I1 plus I2 plus I3 equals 0. The next one is 4. So I figure out, okay, I'm starting up here, and I'm going in this direction. I know I have to be going in that direction because I have a positive 4. So I'm going from little to big on the battery. So positive 4 minus 2I1, so far that's okay. Minus 8, so far that's okay because I'm going from big to little, plus 6I2. That's correct because I'm going opposite the current. So B is right. That gets rid of that answer. Let's look at this other one. 4I1. Okay, I know that can't be right because I don't have a 4 ohm resistor in the I1 loop. So that just goes away. This one is not right. So that gets rid of these two. And now D, 8 plus 2 minus 6I2. Okay, so I'm starting here, going in this direction. I'm going to this 2-volt battery. That's right so far. And then I come up here, minus 6I2. It's negative. It has the right current. So that one is correct. So it's B and D. That's how you'll approach when you get a question like that. You'll just go through each equation, find where it starts, and then go through and ask, okay, are all the signs right? And are all the subscripts right? You're looking for signs and subscripts. Is it positive or negative? Is that correct? And is it I1, I2, or I3? Okay? What else? Megan?
On 16, can you show what currents go into each junction?
Yeah. So here, you don't know all the currents, but I just sort of pick the closest junction. I think this one has to be done here. Let's see, I forget. So look, I have 12 amps coming in here and 4 amps coming out there. That means that this junction, or this part of the wire, has to have 8 amps, right? Has to, because I have 12 coming in, I have 4 going out, I have to have 8 going out the other one. So I'm almost close to the answer, because I have 8 amps coming in, 5 amps going out. So I have to have 3 amps going there. So it has to be 3 amps. I think you can address it on this other side too. Let's see. You might not be able to. No, you don't really have enough information from that other junction. You have to approach it from right here. Okay? But usually, if you have this question, it's going to be a 2-step process. Figuring out the current coming in here, and then figuring out the current coming in there, just like I just did. Okay, Megan? Sonia?
So for the multi-loop ones, when you go against the current, it's positive, and with the current, it's negative.
Right, so if I remember those rules I gave y'all, that if your current is in this direction, and I'm traveling in this direction, that is a negative IR change in potential. But if my current is in this direction, but I'm traveling in this direction, and we had two directions, your current direction and your traveling direction. What direction are you going around the loop? My change in potential is positive IR, which is different from what you would expect for a resistor, but you're going opposite the direction of the current, so that's why it's different. Reviewing those rules would be helpful if you're weak on those multi-loops. Rob? Sure. Okay. Note the different voltages on the battery. So if I put a note in parentheses, that's probably pretty important. So note here that this is 2 and 2, but this is just 1. On something like this, I like to just think about what are the voltages on every bulb, and then I can go back and figure out what the answer is. So I know that these two split that voltage V, so they get V over 2. Here, these three split up the 2 volts, so I get 2V over 3, 2V over 3, 2V over 3. Right, they're splitting 2 volts 3 ways. On this last one, first of all, I get 2 volts here, and then I get 2 volts across these 2 bulbs in series, but they split up those 2 volts into 1 volt and 1 volt. So now I want to do DC, B, and A. The one with the, I'm going from bright to least bright. The one with the biggest voltage is D. That doesn't help me anywhere. But I see that D is not equal to C, so I can get rid of these. I see that A is not equal to C, so I can get rid of that one. So the answer must be B. And let's just double check that. I have 2 volts. C is 1 volt. B is 2/3 V. And A is V over 2. So that is the proper order. But I would go through and ask, what is the voltage across each individual item? Being careful, of course, here, this one was a little more problematic because we had these different voltages. If I have something like that that's important, I'll make a little note of it in the problem usually. Okay? What else? Exam 3. And this, your exam on the website was missing this part. In fact, it had been missing all the pre-response, but I uploaded it a couple days ago. Yesterday? I don't know. Recently. But it didn't have question 1 because it was on the bubble form. But I'll send this out to y'all, this document that has all of the exams. I recommend that you print them out and practice them over and over and over again. Many, many times. How many times do y'all practice these exams? Once? Twice? 3 times? 12 times? The more you practice, the better. All right, any particular ones here? It's exam 3. We did RC circuits, household circuits, magnetic fields. Yeah, Courtney.
Can you explain how you got the answer for the 6, please?
Okay, so an electron, well, the force, which is what I'm looking for, the magnetic force, is equal to QVB sine theta. And they're moving with the same speed, in the same direction, and they have the same charge because they're an electron and a proton. So this is the same, and this is the same. So that means that the force is going to be the same in magnitude, except that the signs are different. So when the signs are different, they're going to be opposite in direction. You might have put A. That's a good answer. It's still wrong because they do have identical magnitudes, but they're opposite in direction. The masses don't matter. The masses are important for acceleration, because you know acceleration is F over m, the electron will accelerate at a much bigger rate, but it experiences the same force. David? Sure. Okay, yeah, a lot of people tripped up on this one. When I have total internal reflection, I have a light ray that comes up to a medium. It's important, first of all, that the index here, N1, be bigger than N2. That N1 is bigger than N2. In fact, that's sort of the principle behind this question. That's where you would get to the correct answer, which is the cladding is bigger than the core. The index for the cladding, which is really just this material that's over the actual fiber optic cable. Fiber optic cable is a plastic, transparent material that the laser travels through. The reason that the index N1 has to be bigger is that you want this light ray to bend away from the normal when it comes into this new medium, such that it's going to bend in this direction. And in order for that to happen, think about our wave fronts like this. You want it to speed up here so that it bends in this direction. Remember our tank, our twin propeller boat, that you make one side go faster than the other? If I make this side go faster, it's going to turn in this direction. And so in order to get total internal reflection, I want it to turn away from the normal, which means that this index needs to be bigger than this index of refraction. I always think of, I think, did I show you all that little plastic tube? I brought that to class, where it had the total internal reflection, the green laser went through it. That is plastic surrounded by air. And in that case, the cladding is air, right? You don't have to have a cladding over a fiber optic cable. You can just have it in air. They just put it on there to protect it from nicks and stuff. So my cladding always has a lower index of refraction. Okay? What else? Okay, good. Oh, 16 right here? Yeah. So here I have reflection. The important thing here is that theta I equals theta R. And then also that your angles have to add up in a particular way. Triangle has 180 degrees. A right angle has 90 degrees. So here, first of all, it reflects off of there. This angle has to be 40 degrees by the law of reflection. That means this angle has to be 50 degrees, right? Because 50 plus 40 equals 90. Then notice that I have this triangle right here. So this angle has to be 180 minus 90 minus 50. 180 minus 90 minus 50, that's equal to 40 degrees. So if that angle is 40 degrees, that means this angle has to be 50 degrees, and then that's going to also be this angle, 50 degrees. So B is the right answer.
I think that 20 that we just did, I think the C on that answer key. Is it?
Oh yeah, it should be C. Yeah.
You said it correctly.
I said it correctly. Yeah. But I'm not taking the exam. Yeah, just be careful, because I've seen students, they make mistakes like that. Because I've been rushing through it. You should have plenty of time, 2 hours, right? 2 hours should be plenty of time, even though it's a longer exam with roughly the same number of free response, a little bit more maybe, and then roughly twice the number of multiple choice. Should be plenty of time. Wow. Don't bring a beer or anything and take a break. You can't bring beer into the classroom, first of all. Don't do that. Sorry, don't tell anybody I said that. But just work diligently. Know how to do it and be careful. Okay? Other questions here? Yeah, Megan?
You explained 12.
Yeah, a lot of people miss this one too. Which this question isn't any different than the questions where I have a particle that's just going like this, right? You remember those questions and I ask, what is the sign of that particle? No different. Let's just pick apart. I'm just going to say, I'm going to look at this section. Here I have a velocity that is in that direction. I have a force that's in that direction, and I have a magnetic field that is into the page. And let's see, what is the sign of that charge? Well, V is in that direction, my force is down. That tells me, or rather V, that should be experiencing upward force, but instead it experiences a downward force. So that means it should be negative, right? If I have a velocity in this direction through a magnetic field like that, that should experience an upward force, but it doesn't. It experiences a downward force. That means my particle is negative. And I just took this little section right here, right? It's moving in this direction. It feels a downward force. But people are tripped up because it was the whole circle. I think that's what tripped you up, right? Yeah. But that's what happens in a cyclotron or a mass spectrometer, that you have this particle that's trapped in this circular path, and you measure the radius of that path. Courtney?
How are we going to be able to, I guess, like, I was one of the ones that fell trapped in this one. So what I did is I used the second rule, the one where you put the thumb in and then you spin your hand. How are we going to be able to tell the difference between one of the first right-hand rules and the second one?
Okay, yeah, that's a good question. I guess I hadn't thought of that, but that's what tripped people up, because you're used to seeing that loop. The loop is for a loop of wires, though, right? And this is for a particle moving through space. And when I'm looking at the loop, I don't think of a force on the loop. Like, we never consider the force acting on the loop. It's always, what is the magnetic field that's generated by the loop? I can see that you would be confused by that. But I still defend the question, because I think you understood it. You were just tripped up by it. But those are two different scenarios. Okay? Sonia?
So how do you know it's going down?
How do I know it's going down? Well, if I look at my particle, like I said, I'm just picking a point. I'm saying right here, for example. You can take any point. I'll do another one here in just a second. So the velocity is right there. But because it follows this downward path, the force that's acting on it, which is a centripetal force, is in that direction. Okay? Let's look at another scenario. I saw your hands up. Yes, let's say I pick a different point. Let's say I start right here. My velocity is in that direction, but my force is in that direction. So if I have a velocity that's up, the magnetic field is into the page, the force should be in this direction, but it's not. So that means it's a negative particle. Okay, there were other hands up. Emily?
I had a different question, like not pertaining to this one.
Okay, were there other questions about this one?
I was going to ask, like, so if the force is negative, then the sign of the charge is always, like, if the force is down, the sign of the charge is negative?
No, like it matters the direction of the magnetic field. If I switch the direction of this magnetic field, then this would be a positive particle. And don't try to memorize scenarios. That never goes well for students. I know you think there might be a limited number of scenarios, but there are enough to just trip you up. Emily?
Can you go to number 8?
The Earth's magnetic north pole is at the geographic south pole. That's true. Right? Remember we talked about, here's the Earth, there's North America, there's South America, there's Europe, Africa, here's Antarctica down here. That this is the geographic northern pole, but it's the southern magnetic pole. And we can think about this, because if I have a magnet over here, like this is my compass, the north pole of this compass is going to point towards the north. It's going to be attracted to the southern magnetic pole. And the south pole of that compass, right? A compass is just a needle, right? A magnet that's like a needle. The south pole is going to point towards the northern magnetic pole, which is the southern geographic pole. All right, the poles are switched in Maine. magnetic fields are caused by moving charges? Fundamentally, yes, that's correct. That when I have a moving charge, that generates a magnetic field. Wood is not magnetic and does not have any moving charges. It's sort of true, right? That wood is not magnetic, but it does have moving charges. And that gets into our idea of magnetic domains. That wood has these magnetic fields within it, but its magnetic domains are oriented randomly so that it's not magnetic. It does have moving charges that each generate a little magnetic field, but because they're all oriented randomly, that means that it's not magnetic. So 3 is sort of right, but not true. So it's 1 and 2. Okay? I like those 1, 2, 3 questions, don't I? What else? We'll look at the next exam. If y'all need to go, I know it's 4 o'clock, but I'll be here as long as you need. Lauren, let me just make sure I got you. Huh? Oh, okay, it doesn't really matter, yeah. But I do have you. Oh, you too. Okay. Oh, did I have the free response on this one? Oh no. Is the free response for this exam on the website? It's on the video, I know. I'm sorry. I will upload that and send it to y'all over email. Y'all should tell me this. Not that it's your fault, but so that's exam 3 and 4, or exam 2 and 4? I think it was 2. I'll make sure you get it over email. Okay. You want to look at the free response, David? Number 13. Okay. If we want to look at the free response, I can pull it up on the video and just get the text from it. Okay, number 13. So here, I want to know what is the path length difference. If I'm right here, the path length difference is 0. And then as I go out, 1, 2, 3, I increase by wavelength increments. So this is 1 wavelength, this is 2 wavelengths, this is 3 wavelengths. So my path length difference here is 3 wavelengths. Now if I'm looking at dark spots, it's not full wavelengths, but it's half wavelengths. So like for example, if I'm right here, the path length difference is a half a wavelength. If I'm right here, it's 1.5 or 3 halves wavelengths. Right here will be 5 halves, right here will be 7 halves, and on and on. So bright spots, the path length difference are wavelength increments, 1, 2, 3. Bright spots are half wavelength increments. And that's borne out on the equation, which is on the website, on the equation sheet. D sine theta, that's your path length difference, is equal to m lambda for bright spots, is equal to m plus 1/2 lambda for dark spots. There are subscripts on theta for bright and dark on those. So if you forget that, you can look back at those equations. Courtney? Okay. Okay. Which would make the central maximum bright spot narrower? I always write the equation first. I recommend that you do too. I mean, I can't really remember the relationship. It always helps me to write the equation. In fact, the more you write, the better you'll do in the exam. If you come into a question, you just have no idea what to do, just write down the equation first of all as a good first pass, and then begin to think about, okay, what are my relationships, or what are the value that I'm looking for if it's a calculation type problem. Just write something, just do something, even if you're not really sure what it means at first. So here, if I increase the wavelength, that means that theta is going to increase, because the width of that bright spot, really, I'm asking about theta or I'm asking about y. So it's not increase the wavelength. That makes it wider. If I increase the slit width, that is, if this gets bigger, this gets smaller. So 2 is right, increase the slit width. And then if I increase the distance from the slit to screen, now that's L. So I look at this equation, y equals L tan theta. If I make L bigger, that means y is going to get bigger. I'll draw a picture of that, but so that means that the bright spot gets wider, so the answer must be 2 only. Let's go back to this, because here you might be confused because, oh, but why didn't I, if I make L bigger, why doesn't theta get smaller, right? Why does that not apply there? Let me show you. So this is my single slit, and I'm going to put my screen right here, my bright spot here, and then my light is originating here. So I have these angles that are coming out like this, going to those dark spots. Notice what happens if I just move my screen back. These light rays continue, but they diverge. That means that my dark spots are going to be here and here. See, that's a wider bright spot because I've moved my screen back, and those rays that are creating those dark spots are just diverging. Okay, so increasing the distance from the slit to screen will make your bright spot broader, not narrower. So the answer here is 2. It's a tough question. Rob? Number 18. Okay, so here, the first thing you need to do is figure out the path length difference. The path length difference is 4.25 minus 3. That's equal to 1.25. And then I want to know how many wavelengths is that? This is in meters, but how many wavelengths is it? And one wavelength is equal to 0.5 meters. So what is the path length difference divided by the wavelength? 1.25 meters divided by 0.5 meters. That's what? 2.5. 2.5 wavelengths. So the path length difference is equal to 2.5 wavelengths. That means I get a dark spot. If the path length difference was 2 wavelengths, it would be a bright spot. If it was something else between a half and a whole wavelength, it would be what I call a gray spot, neither dark nor bright. Okay? Find the path length difference, divide it by the wavelength. And then, is that an integer? It's a bright spot. Is it something with a half in it, a 0.5? It's a dark spot. If it's anything else, it's going to be neither dark nor bright. Okay? Important, those are, because that's at the heart of how diffraction gratings, double slits, and single slits all work. And looking at what is the path length difference. What else, y'all? And again, even though the free response isn't up here, I can pull it up if you want. Sonia? Mm-hmm. Okay. The first thing here is to figure out what kind of mirror it is, because I don't tell you the kind of mirror. But since it's an upright and virtual, because all upright images are virtual, and smaller, ding, 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 that tells me it has to be convex. That's the kind of mirror where I stand right here, and my image looks like that. That's a convex mirror. And I know that those have a negative focal length. So the center of curvature is 30. That means the focal length is minus 15. That's the first step that you need to make. Then the object distance is 30. And I want to know what is Q. So now that I've made that first step, this becomes not trivial, but I can make quick work of it. 1 over negative 15 equals 1 over 30 plus 1 over Q. That's negative 1 over 50. So I'm finding the common denominator. Negative 2 over 30 minus 1 over 30 equals 1 over q. That's minus 3 over 30, so q is negative 10. Since I found that it was a convex mirror, I could have gotten rid of this, this, and this. So it has to be either D or E. The reason it has to be a virtual image. Oh, yeah, I got you.
Do concave lenses have also a negative?
Yeah, so convex mirrors are like concave lenses. That is, a concave lens has a negative image distance. Virtual upright smaller in a concave lens. Same type of image as a convex mirror. And vice versa. Convex lenses has the same as a concave mirror. All right? Somebody else had their hand up, is that right? David, did you have a question? Okay. 16? Okay, yeah, so I had to draw this by hand. Hopefully that didn't trip anybody up. It's difficult to make them in PowerPoint with all the little lines. You want to look at each part. So here, I have a positive part and a negative part. And they're going to cancel one another out because they're opposite. It's like a peak with a trough. So it should have a destructive, what's it called? Interference, destructive interference. Next, I have a big peak and a small negative peak. Those are going to add up to give me a small positive peak, like this. Not like this, not like this, like this. So I'm down to either, whoop, no, now I'm just to A. So A has to be the right answer. Well, let's look at these others. Here I have two small peaks that are going to add up to give me a big peak, like this, not like this, or like that. But I've already gotten rid of those options. And then finally, I have a zero peak with a small peak, which gives me a small peak like that. Okay? It'll be similar if you have one like this. It'll just be different waveforms. But you would go through it piece by piece. And as you go along, you can get rid of options if they don't fit with what they should be. Okay? Go ahead.
For number 19, what equations do you have to use? The A sine thing?
Yeah. So you do A sine theta. You find theta for m equal 1. Right? That's for the single slit, that's to the dark spot. So I'm finding theta to here. I'm finding that angle theta. Once you do that, after you find theta, find y equal L tan theta. Then you double y. Because when you find y, you're finding this distance. But I really want to know what is this distance, which is 2 times y. I can work through the numbers if you want. Okay. Megan?
Would there be a virtual object on the exam?
No.
No. Okay.
There wasn't on exam 4. So there won't be on a final exam. She asked, will there be a virtual object? No virtual objects. You want a virtual object? No. They aren't that hard. You just negative. Right? Yeah. You did it last. Okay. Anything else? Okay, well, I'm going to go back to my office and I will send you complete exams. I'm really sorry about that. I'll upload them on the website too, but I'll send a whole document that has all of the exams.